Hello everybody. Welcome to my video on hypothesis testing for independent samples. So let us look at the steps, and you can pause the screen, take a picture, and see the steps I'm going to look at today when it comes to hypothesis testing, as you see. Now, we are looking at a two-sample mean and an independent sample. If we're doing that, the assumptions we need for that are right here. We need random representative samples. I'm hoping whoever collected the data collected it randomly. Got it. 2, we need to talk about the populations being normal or having the central limit theorem to help us or guide us. 3, the pooled variance is only accurate if we have similar variances. So if we're worried that the variances are too far apart, too different, we could also do an F test for the variance to guarantee that. All right, let's get into our problem today. So our problem today, when we're looking at hypothesis difference for the mean one, is right here. We have 60 random people who have responded to our question about how long each day do you use Facebook in minutes. Let us assume the variances are equal. So that's one of our checkpoints. Let's just assume that's equal, just so we can move on in working with the hypothesis test. Got it. Is there a significant difference in the mean time spent on Facebook based on gender? Please perform your analysis at a 10% level of significance. So we go to the Facebook data, and here is our data based on gender, which you can't see. I got to move this over a little bit. There we go. Gender in minutes. So we have gender in minutes broken down in this table. And again, the hypothesis we're wondering is, do we think the amount of time spent on Facebook is different based on gender? So what I like to do is I like to go through my steps of hypothesis testing. Step 1, quickly, to the point. I'm testing to see if there is a difference. There is a difference based on gender. So I'm going to assume the opposite. I'm going to assume there is no difference based on gender. The no is always the opposite of what you're trying to show. We're trying to show that there's an average difference based on gender. So mu1, let's say that's group 1, the male group, and average 2 is the female group. That's what we're testing if you want to put it in numbers. We're testing that mu1 equals mu2. With an alpha level significance, well, let's go back to our question again just to make sure I get it right for you guys. Where is our question? There's our question. No, that's not our question. The Excel has the question. And it was a 10% level significance. Got it. It's very important to know our level significance. 10% level significance. So, how does one do a hypothesis test? Well, to do a hypothesis test, you want to build your critical region. You want to do your test statistic. You want to do all this beautiful information. The great thing about Excel is if you give it live data, it will actually do it all for you. So I'm going to get everything I need utilizing Excel. So how does one do that? Well, data analysis, t-test. Now there are 3 t-tests we have stored in Excel. We have t-test for paired samples. That'll be my next video on dependent samples or matched samples, whatever you want to call them. These are independent samples. That's why they're called a 2-sample test. These are independent samples. Females and males are not paired in any ways. They're just 2 independent groups. So I'm going to do independent. Now, I need to know if we're looking at equal or unequal variances. That's very important when we're doing the formulas. We're assuming equal, as the question said, so I'm utilizing this one. Okay, now you need to scroll in the data. So you go up here, click on this, and scroll in the data. What do I mean by the data? Well, it looks like I'm going to let group 1 be female, so I apologize. Group 1 is female because of alphabetically F is before M. So group 1, variable 1 is female. Just make sure I'm going to make a note of that. Female is group 1. Group 2 is male. So there's the male data. Nice. And so Excel needs to know what is your difference you're looking at. I believe the difference we're looking at is 0. That's the hypothesis. That's H naught. I believe the difference is 0. You need to show me the difference is not 0. But right now, I'm assuming it's 0. What is our level significance, I believe we said one more time, 10%. I'll verify that in my picture. Yep, 10%. If the alphas change, we'd have to update and do this again. And output it. Well, wherever you output it, wherever you pick, make sure that below that spot and to the right is empty, so it can dump the analysis. Really, this is it. Scroll in the X data, scroll in the Y data. In this case, it'd be female, male data. Typically, the hypothesis difference is 0. There are times it's not, but typically it's 0. Level of alpha, that's your choice. In this question is 10%. And then dump it somewhere where it's not going to hurt any data. Click OK, and there we go. There might be some things that says, hey, be careful, and so you should be careful. But in this case, mine clicked out really nicely. And what do we have here? We have everything I'm looking for. We have the t-statistic right there. We have the t-statistic. Got it. We have the critical value. Got it. So we can compare the two. Here, and by the way, this is a two-tailed test, right? We're doing a two-tailed test. It's giving a one-tailed test. I'm not going to look at that. The two-tailed test. The two-tailed test is what I'm looking at because we're looking at a not equal. Is there a difference? So what I look at is I got the critical value. It's right there, 1.67. I got the test statistic. That was negative 2.00. Now, your critical value is 167. Understand, there's two critical values when you're doing a two-tailed test. The upper and lower. All right, the upper and lower. Has your t-statistic exceeded the critical value? It has. The t-statistic has exceeded the critical value. And I'm actually going to write that. My t-stat is lower than my critical value. So what does this mean? I reject H0. If your t-statistic is lower or higher than one of your critical values, if it's higher than the upper bound or lower than a lower bound, you're in the rejection regions. And that's why I'm rejecting. All right, next, my p-value. Where's my p-value? My p-value is up above. Two-tailed p-value is 0.4979, just so you can see what I'm seeing there. 0.498. That's my p-value. All right? Your p-value, you compare it to alpha. Remember, our alpha was 0.1. In this case, my p-value is under alpha. So I reject H0. Notice both ways I reject H0. So bottom line, what is my conclusion? My conclusion is I reject H0 because of above work. But what does that mean? Well, if we reject H0, remember my H0 was, I believe there was no difference. It means I have evidence that there is a difference in gender. When it comes to how much time is spent on Facebook, when it comes to Facebook usage. All right? I have evidence that there is a difference in gender when it comes, a difference in gender usage, okay? When it comes to Facebook usage. And I should say at a 10% level significance. It might change based on significance level. And in fact, it's going to be damn close, but if I change this to 5%, this is still under 5%, but we're talking barely, okay? If we change this to 5% level significance, it's barely under there. I believe the part B was change your level of significance to 5%. What happens? Well, my alpha is barely under it, but we would still reject. And this is where you would need some accuracy to make sure things are good, right? This is barely under 5%. So if alpha is 5%, you still would reject. By the way, if your alpha was 1%, we would not reject. We're not 1% significant. So some people call this p-value double star significant. Double star just represents you're less than 5%. If that number was barely less than 10%, we'd have 1 star significant. Under 5% is 2 star significant. Under 1% is triple star significant. The stars just represent the typical numbers we use, 1, 5, and 10% significant levels. Excellent. All right, guys. Now, we did in the previous video work through all the details. Could we do that here? Of course. If we went back to our first example that we did together, we had this beautiful two-tailed analysis broken down. I want you to know you can utilize that here also. If you don't like doing Excel, you can utilize what we wrote beautifully. So, but there is a caveat. I have to insert. We did not have sum of squares in here. We had a standard deviation 1, and we have standard deviation 2. So we have the standard deviation. See, what we have is the variance, which if we square root, and if I remember correctly, we were talking about the females, but the square root of variance is the standard deviation. The square root of variance is the standard deviation. All right, so these are the standard deviations, the square root of variances. The averages are what are reported over there. The average over here is 79. The average over here is 157. Well, come on, look at the difference in the averages right away. 79 to 157, all right? That is a major difference, right? There's a major difference in those averages. But is it different enough to spring out and reject? The answer is yes, by looking at all this stuff. So the question becomes, all right, what do we do here? Well, we need sample sizes. Those are 30. All right, look over in the summary chart over there, right? Summary charts, 30 and 30. All right, summary charts. What is the sum of squares? Well, you got to understand the formula from our previous video. The sum of squares, what it is the standard deviation of the sample squared multiplied by the degrees of freedom of that sample, which would be n minus 1. That would be the formula, and I'm going to copy and paste that over here. And once we have that, notice what we get, a negative 2036. Oh, look, it worked beautifully. I'm going to get rid of these things because these may not be true for this question. So we get the t-stat. We get the p-value, which we got over there. Notice they match. Notice the critical value has not changed, okay? The critical value, I put it in red because I did not have it written correctly. Well, it's written correctly, but this was written for an alpha of 0.05. Our alpha has changed to 0.1. So what I need to do is think about the picture when it comes to 10%. 10% means we're looking at 95 right there. And so it's a 167 is our critical value, as you see. Critical value matches the critical value. Awesome. So it matches. So that tells me at least Excel is running them right, and it tells me I wrote my codes prior in our previous example beautifully. Now, why would I go back to this? Because notice, I built the Cohen's d in the previous video. It's important to see we have a medium effect size. A medium effect size is when you're above 0.2, but you're below 0.8. So there's a potential of a sample size issue here. Again, we have a medium effect size. We also have the confidence interval, which is pre-built for us. Something that's not over on the automatic chart. So in some respects, my pre-built code is better because I actually see with 95% confidence where the true mean difference is. It's somewhere between just above 0, just below 0, all the way down to 156. There is a potential differential, right? There is a potential differential all the way down to 156. Something's not looking right in my code. So let's visit my code. 95% would be T inverse times K10. Where's K10? K10 is the standard error. I think what's going on is the error is just so vast. All right, the error is 78 points. So if you look at the differential, plus or minus that, it is a major swing. But notice 0 is not in this confidence interval. Since 0 is not in this confidence interval, we should have rejected. Oh, we did reject. Good. Sorry. Got to back it up with my third check. Again, my t-stat is in the critical region, so I reject. My p-value is under alpha, the 10%, so I would reject. Notice 0 is not in this confidence interval, and that's why I am rejecting. So all three say I'm rejecting. And the confidence interval says something stronger. How low it could be. How far of a differential it could be. It could be little. Notice the upper bound. It's close to 0. So there could be close to 0. But there could be a major differential between the two parties. The genders, the females and the males in this study. And that's the test utilizing Excel. The only other thing to talk about in this video would be the assumptions. Well, assumed variances are equal, so we're not talking about that assumption. I'm going to assume they picked random and representative females and males, so I'm not going to talk about that. But I'm going to talk about normal. Both of these are 30, and that means I can apply the essential limit theorem, and I can note that I have normal. Notice both of these are 30. They meet the threshold for the essential limit theorem. So as long as overall things are not too skewed, I'm going to assume normal here. And I need normal because this study is built on the test statistic of T, the T statistic, all right? And because we have the T statistic, everything in here is based on, if you look at the codes, the T inverse and the T dist, you need to have normal. And because both of these are 30, the minimum needed for the essential limit theorem and normal, we are good. All right, guys, thank you for watching my quick video. If you need more details on this, go back to the previous video, example 1 on independent t-test. This was if we had raw data, could we do the independent t-test quicker? The answer is yes. Excel has it pre-built in based on if you're assuming equivariance or not. You need to understand what you're assuming in the question to run the test. And then once I have the test, it's just a matter of checking the typical things you do in a hypothesis test. All right, guys, thank you for watching this video. Stay tuned for others.